In this video, we present the controlling of the quadrotor with reinforcement learning. We use reinforcement learning techniques to train our control policy. Two neural networks are used during training, namely a value network and a policy network. The value network is a function representing how good a particular state is. We use this network to guide policy training. The policy network is what actually controls the quadrotor. Given the full state, it directly outputs the thrust forces to be generated for each rotor. The two networks are updated at every learning iteration. Each learning iteration consists of exploration, a value update, and a policy update. During exploration, we mostly follow the current policy in order to evaluate the value of the visited states. However, if we only use the current policy, it is unlikely to find a better policy. Therefore, from time to time, we add noise to the action in order to observe the outcomes of actions different from those of the current policy. After obtaining data from exploration, we update the value function. The value function lets us interpolate the data so that we can estimate a value for any currently unvisited state. Every time we add noise, we accumulate a pair of trajectories, one that followed the current policy and the other where we added noise for the first time step. The two paths are evaluated according to two sources of information: the costs it observed on a trajectory and the value of the state where it ended up. The policy is updated towards the better of the two in a given pair. Training is performed in simulation, where we can train the networks in a fast and safe way. In simulation, we place a quadrotor in a random configuration and velocity. The goal is to approach the red point as quickly as possible. We can see that over more iterations, the performance is visibly better. However, performance did not significantly change after 200 iterations. But we simply use more iterations because training requires a relatively short time. Without any parameter tuning after training in simulation, we deploy the trained model on a real quadrotor. Here, we simply demonstrate that we can give a position command to the quadrotor. The policy can also handle disturbances that it was not trained on. The most notable feature of the policy is its stability. It can stabilize even in very challenging configurations. Here we demonstrate this by throwing the quadrotor into many different attitudes and velocities. It also works when it starts nearly entirely in an upside-down position. This hand launch process is very repeatable. With similar launch velocities and attitudes, the quadrotor almost always stabilizes. With a higher or downward launch velocity, we sometimes observe failures. These failures are mostly due to the physical limits of the hardware and the size of the experimental area.